see you all back again for the fifth of the Compton lecture series. You never know if there's still someone who hasn't been before, but my name is Wyman, and I'm doing the lecture series this fall on the subject of cosmology. I'm a theoretical cosmologist here at the University of Chicago, and the subject of today's lecture is structure, which is basically going to be a lecture about dark matter. Before I start my lecture, though, I wanted to advertise someone else's lecture. This guy is John Mather. He won the Nobel Prize a few years ago for actually the subject of last week's lecture. He was one of the two people who designed the Cosmic Background Explorer telescope that discovered the microwave anisotropy. So he's going to be giving a lecture on many of the same things that I'm talking about next Tuesday. And it's possible that the tickets are already sold out. I have no idea, but I thought I should mention.
No tickets.
Do it?
I think it's no tickets.
No tickets. So you just
show up and wait in line.
I see.
5:30.
Is it 5:30?
5:30 the door opens.
Oh, I see.
Point of order. At the same time, Lisa Randall will be talking about the same thing at the Harold Washington Library.
Oh, really?
Same date, same time.
Well, I'm that plan. Well, I'm not going to be either, so. That's really interesting. Okay, I didn't know that Lisa Randall was even going to be in town. Anyway, so that's next Tuesday. And there's also information on the handouts. But just to carry on, today's lecture, we're finally making some progress. So those of you who have been here for the previous lectures will know that my sort of plan is to travel through the history of the cosmos, pictured here on this sort of projective timeline. And so someone pointed this out to me, that this timeline is in some ways inaccurate. It's not really a surprise if you're not going to capture the entire history of the universe on a single 2D slide and capture everything in it, or else our field would be a lot simpler than it is. But anyway, the point is that the first three lectures, we passed the first one. We were really focusing way over here, the early moments of the universe, and that's because lots of stuff happened then. Obviously, we didn't have spent 3 whole hours talking about it without there being plenty to say. But the next few billion years, which is basically, I'm going to be talking about basically the full history of the universe between the release of the CMB and, in a sense, up until the contemporary time. And that is whenever all of the stuff we're familiar with got going. So essentially when we started with these ripples in the CMB, and those ripples in the CMB were operated on by the gravitational force to basically build up all of the structures in the universe, the large-scale structures, what we call it, that host galaxies, stars, planets, black holes, all of the things we're familiar with or made out of the stuff that we're familiar with. So before I get into structure formation, let me remind you about what dark matter is. And those of you who were in my first lecture may remember that I singled out the discovery of dark matter as one of the 3 key discoveries that have helped to shape our modern understanding of cosmology. And dark matter is the oldest such discovery. The other 2 were cosmic acceleration and the inflationary thought, which were discovered, or at least demonstrated to exist only in the past decade or so. Whereas dark matter was actually found in was actually definitively proved to exist in the 1960s. And so what they were doing in the 1960s was, there's a lot of astronomers around, and they were studying galaxies. Galaxies are great to study because they're bright, they're complicated, they're big on the sky, we can resolve them even back then. And one of the things that astronomers were doing with galaxies was using observational techniques to figure out how fast the stars were going around the galaxies. So you can do this basically by using the spectrum of the light, or the characteristic pattern of light that comes out of the stars. And then basically the stars that are coming towards you on one side of the galaxy will be moving towards you and therefore will be slightly blue shifted relative to the stars on the other side, which are moving away from you. And so you might think that's a really tiny difference, and it is. But it turns out that we can do these spectroscopic measurements, these measurements of the wavelengths of the light coming out of the stars extremely precisely, and therefore can determine how fast these stars are going relative to each other. And so the reason why this is of interest is because whenever you're trying to learn about galaxies, and in the 1960s, astronomy was still very much, it was a field of sort of in the naturalism phase, where you're just trying to figure out the variety of what's out there. We didn't really understand a whole lot about how galaxies were formed or how the universe evolved. But it made a lot of sense to look at galaxies one at a time and try to figure out what each kind of galaxy was like and figure out what kind of properties they shared. And so one of the things that you wanted to know was how massive a galaxy is. Now, we know that the orbital speed or orbital period of stars around a galaxy is correlated to the mass in the galaxy. And we know that because the gravitational force tells us. And in fact, perhaps the oldest law of astronomy is Kepler's law, which is what's plotted here, this blue line, which basically Kepler's laws of whatever the word is for going around the sun.
Planetary motion.
Planetary motion, thank you. Sometimes I forget these things. So Kepler's laws of planetary motion more or less amounts to the statement that if you have a mass at the center, whenever stated in modern terms, you have a mass at the center of the sun, this is determining how all of the planets move. And then the farther you go out, basically the slower you go. And then that speed follows this simple law. And once Newton comes along and tells you what the force law for gravity is, you can turn this curve and turn it around and use it to find out how much mass there is in the sun. And so for a galaxy, you should be able to do something very similar. So in the 1960s, they knew very well that most of the stars in a galaxy were in the middle, in what they call the bulge. And so they thought, well, if we just measure the stars in the outskirts, then we can just see how fast they're going, and that will tell us how much mass is in the middle part. And that'll be a way of telling how massive galaxies are. But when they actually did these measurements very carefully, they found that Kepler's laws of planetary motion were not at all the right description for the laws of solar motion or star motion in a galaxy. And indeed, in a galaxy, we always expected something cutting to happen in the center because that's where all the mass was. But rather than slowing down as you go out to higher and higher radii, to further to larger distances, but the opposite thing happened. Well, is that the stars at the very farthest parts of this galaxy were moving just as fast as the ones close in. And so, and in fact, sometimes the further ones out are moving even a little bit faster, as this plot seems to suggest. This is a plot made of our Milky Way, but you could make these plots for for every spiral galaxy. And so what this means is that most of the stuff in the galaxy is not the stars. The stars only represent a small fraction of material in the galaxy. And for you to have a rotation curve, because that's what this is called, that's flat like this, in fact, most of the matter in the galaxy has to be in an area even bigger than the observational disk of the galaxy is. And so this is our modern picture of what a galaxy looks like. We have a bright disk in the center spinning. But then we have a very much larger, what we call dark matter halo, that's a spherically symmetric, approximately spherical collection of dark matter. And in the part where the galaxy lives, the dark matter is simply, you're just getting more and more dark matter as you go out to larger and larger radii. And that's why you have this flat rotation curve. And it's worth pointing out that this is one of the co-discoverers of this was Wyman, who is a now very famous astronomer. And she was also a pioneer in astronomy because astronomy actually now is a fairly gender balanced field, much more than many of the sciences, but she was quite a pioneer in the 60s in doing these observations. And so it's often a good thing to point out. She did that. However, dark matter was actually discovered in the 1930s, as no one appreciated it then. So Fritz Zwicky was, in the 1930s, studying another kind of galaxies called elliptical galaxies. Now, elliptical galaxies we now know that elliptical galaxies are what happens when two spiral galaxies smash into each other. And they don't have a nice spiral structure. They're just a big collection of stars that look like a big egg that tends to be ellipse or elliptical galaxies. And Zwicky was a really clever guy, and he was looking at how fast the stars are moving in elliptical galaxies. And he said, there's just no way that the stars are, the number of stars there can account for how fast the stars are moving, because essentially the more mass there is there, the faster motions are. And so he said, there's some matter missing. And so he was a smart guy, but he was a bad namer. Missing matter is just a boring name, and it's sort of embarrassing. Whereas dark matter sounds exciting and fun. And so everyone sort of ignored Zwicky's missing matter for a long time. And part of that is that the field wasn't really ready in the 30s to confront the existence of dark matter, I think. But I think I do think that nomenclature sometimes affects things. And having a good name that captures both that captures the effect can lead us to think about it more than a bad name, like missing matter that just sounds like you made a mistake in your calculation. So I wanted to give old Fritz credit where credit is due. And so I said that today's lecture was about structure and dark matter. The structure part of dark matter is, again, this formation of the structure of the universe. And we have a picture now that we call hierarchical structure formation, which is an account of how dark matter, how the little ripples of dark matter that are matched to the ripples in the CMB, the cosmic microwave background radiation that we discussed last week, how those ripples grow up to make galaxies and clusters of galaxies like we see today. Because it's actually a really hard problem to go from little tiny ripples that are just a few parts in a thousand of deviation from homogeneity to the state today where we have very dense things like the Earth or stars or these galaxies, and then big areas between that are empty, very low density. And so it turns out the way that happens is basically breaks into two key components. One is that those little ripples, so the ripples of various size, all collapse at the same rate. One of the facts about general relativity is that it's a scale-free theory. So the law of gravity doesn't know anything about length scales. It treats big things and small things just the same. And so if you rescale the equations appropriately, you could describe a big sphere and a little sphere using exactly the same formulas. But the small spheres are smaller, and so their characteristic time for them to collapse is a lot shorter than big ones. And so this is one part of the hierarchy of hierarchical structure formation, is that the smallest overdensities or halos are the ones that are first to collapse. And by collapse, I mean become dense enough that they act as a combined unit rather than as part of this collective. Because this is the key transition that happens, is that initially the universe is smooth and expanding with little ripples in it. And then as each of those ripples gravity grabs each ripple and starts to contract it. And there's a special place we call collapse. Whenever the density in a particular ripple is high enough that it breaks off from the expansion of the unit space around it and forms into a single compact unit. And it turns out that we know that the number of the critical overdensity is about 1.6 something. A few of the decimal places we know. And so that whenever a ripple gets to be 1.6 times as dense as the space around it, then that's the special place whenever it starts acting as a coherent unit rather than as a wave in the background. And so the small coherent units clump first, and the bigger coherent units clump later. And so as time goes on, if you look in the very distant universe and say what halos have formed, then you'll typically say small. And then if you look at the modern universe and say what halos are important now, and then the answer is much larger ones. And so that's the correlation of time versus sort of dominant halo size. The other aspect of that is that to make the very big halos, the big clumps of matter, you actually assemble them using a lot of smaller ones. And so what you have is that within a very big cluster, or a big halo, that is actually formed by taking a lot of these little subhalos that collapsed earlier, and they all collapse together into an even bigger unit. And so those are the two key components. Collapse of small things, and then those small things then gather into bigger things. And so when we do computer simulations, what we get is a picture that is sometimes called the cosmic web. And even though I've been drawing spheres up to now, these spheres actually have an additional structure that is known as a filamentary structure, which is why it looks so web-like. And so essentially along these filaments, these lines, there's many of these little halos, these approximately spherical clumps, making up these filaments. And then those clumps then flow along the filaments to make the big nodes, which are the largest clusters. And so that's the way that the procedure goes through. And so this is from a computer simulation. Both of these pictures are from a computer simulation run in Germany called the Virgo, by a group called the Virgo Consortium at the Max Planck Institute. And so these are amazing simulations. And so you can really zoom in. So you just take one of these clusters, one of these nodes, and you can zoom in, and what you see is exactly the picture that I was just describing, of this hierarchical structure formation. So this big clump, this big halo, is composed of many smaller halos that have all fallen together as the universe has gotten older. And so we can actually show this in a movie. Now, one of the things I said in the very first lecture is that as we've come to understand cosmology better, we can take the discrete time steps or pictures that we have, and using our knowledge of the underlying laws, join those discrete pictures into a film. And I think I may have showed this movie in the first lecture, but it's really remarkable to me that we can make these computer simulations and then compare them to the real world to see that our computer simulations really do look like what we see out in the night sky or in the distant universe. And so we really have hit on something. We really have hit on the right description. And so this is a picture. So this is starting when the universe is quite old. So this is a redshift of 28.62. I don't know why they chose that very specific number for this movie, but so the universe is about 1/20, about a 30th of its current size in each direction. Whenever this movie is started, you can see the movie, at this point it's still just small ripples. Each of these blue dots represents a clump of matter. And what will happen is these clumps of matter will form. First, the smallest clumps will gather together, and those small clumps will form into the large scale structure. So you can see it happen in real time, not in real time, much faster than real time. It's about 10 billion years or so. And so you see that whereas you started with a bunch of small clumps that had no discernible structure, that at the end you find very discernible structure, where you have the big clumps that have formed up, and then big voids or empty areas that have been left behind. So now that we have this very theoretical idea about how dark matter gathers together, what are the consequences of this behavior of dark matter? And up till now, by the way, all of these simulations are just dark matter. There's no regular matter in them, just for these, because it's a lot harder to simulate regular matter than dark matter. And so one of the things we always have to go back and check is that we can do our simulations using only dark matter, and then put this regular matter in at the end in a way that's consistent, and that the answer is the same. And that's a complicated story, actually. But so one of the very first consequences of this hierarchical structure formation story is that you might say, one of the questions we'd like to answer is, what are the first things to form that make life? What are the first structures of ordinary matter that are made? And in the hierarchical picture, the first things to collapse are small things. And so we should expect then that these small halos will host individual objects, which will be the first things to form. But we don't yet know which are the first, we know and there are two things that basically get formed in the very early universe. There are black holes, and there are stars. We think that we're pretty sure that there are stars forming out there. We've never seen one. So they don't live for very long. And so basically, let me just go through these a little bit slowly. So a black hole in the early universe is called a quasar. And it's called a quasar because whenever a black hole forms in the early universe, and this happens later on too, but particularly then, it's in the middle of a forming galaxy, a nascent galaxy, and it's surrounded by lots of gas. And that gas, after the black hole forms, the gas falls into the black hole. And that infall process, even though the black hole itself is dark, generates a tremendous amount of light. And we know now that what happens is that not only is the whole black hole just sort of glowing, the area around the black hole glowing, but the majority of the energy is shot out into parallel jets going in either direction. As the matter falls in, the black holes are generally spinning, rotating, and all of the stuff around the black hole is spinning, and it falls into the top and bottom of the spinning direction, and most of the stuff just goes straight in, but then it loses a lot of energy and a lot of the energy gets shot straight out. And so these jets are so bright that we can see them across the entire length of the galaxy, billions of light years. We can see these from 10 billion light years away. And they're sufficiently bright, even at tremendous distances, that they're called quasars because they're quasi-stellar objects. They look as bright, they look like stars. And they look like funny stars, which is why they weren't just simply identified as stars sub legere. But they're as bright to us as stars in our own galaxy are. So they're an amazingly bright thing. And so this is one of the things that we know forms in the early universe. But there's also a speculation that the first generation of stars is formed. Now again, this is another one of these times when cosmologists get their time backwards. And so we call the first stars to form the population 3 stars. Population 1 stars are the stars around today. And so for most of the history of cosmology, we thought of the past as we sort of start from ourselves and go out to the past, because it's looking out into the distance. But of course it's older. But population 3 stars are the earliest stars. And so a lot of people think that there was this early generation of stars that were much huger than the sun. So I tried to give an indication that, so here's a picture of the sun versus a red giant. And so red giants are very, very big. Now a population star would have been much, much bigger even than red giants. They were enormous, hundreds of times the mass of the sun stars. And they would burn out in a few million years. So they were incredibly intense sources of energy. And so one of the reasons why we're interested in these first objects is obviously, one, just to get the story right, just to know what happened in the history of the universe. The other thing is that we know that at some point the universe became ionized, because the universe today is ionized. The universe became ionized, and so most of a lot of the gas had its electrons knocked off of it, and so that there's just bare ionized gas. But in the very early universe, whenever the CME was released and the universe was cooling down, we know that the universe was neutral, that the gas was deionized. And so something had to take the gas from being neutral to being ionized. And what that was what we figured that it was is that the UV light that was released from whichever the earliest objects were created were, then just made these, started shooting light into the gas of the universe, and that UV light would cause each of the atoms to be ionized by just having the strong, powerful photons knocking the electron off. And so it's actually a very, we still don't know exactly how ray ionization took place. But by studying this, we hope to observationally study this time whenever the universe went from being neutral to ionized. And then we can hopefully then connect that to figure out which of these objects was more common in the very early universe, and which of them made the most, was the most efficient source of energy. Because it's an important question. And it's also important, just interesting to note, I think people generally are interested by black holes, including me, and is that whenever these first quasars appear, they're huge. They're thousands or tens of thousands of times the mass of the sun. But we don't know really very well how they went from 0 to 10 to the 5 in size. But we're pretty sure they weren't. We know the early universe didn't have a whole lot of really big black holes. But then, a few billion years later, we start seeing black holes popping up. And somehow, over the course of a couple of billion years, they've managed to gather tremendous amounts of mass. And so, we don't know how that happened exactly. And people have good theories about it. But it's still a very, it's a hot area of research. And so, if we knew more about these quasars and their abundance, we might know more about how black holes were initially formed. So the last consequence of this hierarchical structure formation picture is the one I was alluding to before, and that is that once we understand where the dark matter is and how the dark matter clumps together, then that will give us, we hope that will give us an indication of how regular matter or light-making matter is clumped together. And so this is where we have to go through a feedback process, because we use our simulations to figure out how the dark matter behaves. And then we make our best guess and do calculations to figure out how the ordinary matter attracts the dark matter. And the dark matter will essentially, because of its gravitational force, pull the regular matter in. But then we have to look out into the observations and see if we got it right, and then go back and fix our simulations so that we get the right match between the dark, with how the ordinary matter should behave. And this is actually a really tricky problem. Especially, so in the outskirts of dark matter halos, we pretty much know what's going on, because there's most of the ordinary matter that's clumped in the middle. But the question is, what happens in the middle of these dark matter halos? It's the trickiest bit, because that's where most of the ordinary matter is. And it's just worth saying that part of the reason why the ordinary matter gets stuck in the middle, whereas dark matter doesn't. So remember that ordinary matter dark matter has no friction. Whereas ordinary matter does. If you get two gas clouds and you bang them together, they run into each other and heat up. Whereas if you take two dark matter clouds and bang them together, there's no bang, they just shoot straight through each other. And so that's why ordinary matter makes these nice galaxies, or these disks, because the process of collision releases energy, whereas the dark matter stays in these nice, almost spherical shapes, because it doesn't have any efficient ways of losing energy. So, I said that we should then look at observations. So the best, maybe not the best, but one of the key important ways of observing the properties of large-scale structure and therefore of dark matter is to look at galaxies. So in the 1960s, we're studying individual galaxies and trying to understand their properties. In the 1990s and 2000s, what we really want to do is collect tens and hundreds of thousands of galaxies and look at their statistical properties. And so there have been some very big, what are called galaxy redshift surveys to do this. And this is a picture of Josh Freeman. I actually went to get a better picture of him. This isn't very flattering. So if you know Josh, I'll apologize for me. Maybe But he runs the Sloan, or for a long time has run this, I'm not sure if he does anymore, but for a long time ran the Sloan Digital Sky Survey, which was basically used as Apache Point telescope in, I believe, New Mexico, to systematically survey the sky and take pictures of galaxies. And then for each galaxy, you find out how bright it is, and critically, you figure out how far away it is by measuring its redshift, the distance the light has traveled from the galaxy. And so with that information, you say, you know, where the galaxy is on the sky, how bright it is, or you can measure some properties about it so you can have a sense for how massive it is. And then, with its redshift, you know how far away it is, and so you can make a 3D map of thousands and thousands and thousands of galaxies. And so what you might notice as you look at this 3D map from the Sloan Digital Sky Survey, or this 3D map from what's called the 2-degree field redshift survey, which is done in Australia, is that this pattern of where the galaxies are, with these nodes and filaments, matches exactly what our computer simulations said they should be. That the galaxies are in fact following dark matter. We have the right picture, at least qualitatively. And so now we just have to see how, now that we have the right qualitative picture, it's a matter of getting quantitative grasp on this very particular pattern. But so the Sloan Digital Sky Survey is made up with a nice video where, since it's a 3D map, we can just start at the center where we are and zoom out through all of the galaxies. And so each galaxy you see here is an actual image of an actual galaxy placed in its actual, in its true position relative to the Earth, which is at the center, which we're moving away from. And so we have this amazing three-dimensional map of the galaxy. And as you can see, as you get further and further out, the galaxies get redder as they're redshifted, or some of these are just intrinsically redder galaxies. So we can actually do this thing where we can do a three-dimensional tour of the millions of light years around us, because we have this amazing map, this 3D map of where all of these galaxies are. I just think that's really remarkable. That's from the Sloan Digital Sky Survey webpage. And something I mentioned in my first lecture, and I was just alluded to before, is that we can use these observations to test our theories. Now, Einstein's theory of general relativity is a very good theory of gravity, obviously. But basically because of some of the mysteries associated primarily with the dark energy, which will be the subject of next week's lecture, the fact that the universe's expansion rate is accelerating today, this leads many of us to think that there might be some new component beyond general relativity that is causing this accelerated expansion. And so if that's true, then we have to change the theory of gravity a little bit. But we can't just do this willy-nilly, because, as I told you, the simulations we do of general relativity match the observed universe extremely well. So we have to do simulations using these other theories, which are not radically different from general relativity, I should say. We still have to test them. We have to test them as rigorously as we test general relativity. And so what we can do is do these simulations using both laws. And this is one from my own work, where I compared the same. So you start with the same C of E, the same initial ripples, and you advance the universe to the modern day using the two different theories. And you can see that the same structures are present. So there's a big clump here in this picture. There's the same big clump here, but in this particular modification of gravity, the gravitational force gets stronger today than between galaxies than in general relativity. What that means is that you get bigger clumps, and the gravitational force makes structure form more quickly. And so then you can imagine going out into observations and trying to tell the difference between a universe that looks like this and one that looks like this. And so that's one of the things that we do in our research. And as nice as these pictures are, we actually, to do the comparisons, we use statistics. And those statistics are not so different from the statistics that I described for describing the cosmic microwave background radiation, where we basically do a Fourier space decomposition of of the patterns of where these galaxies lie. And so here, these points are in fact that very decomposition for the Sloan Digital Sky Survey, where the correlations between galaxies are captured here. And you can see that it's a lot harder to describe the galaxy properties than it is the CMB. Because remember, for the CMB from last week, our theory prediction was a dark line, and it pretty much nailed every point. Whereas for the galaxies, you see our straight line doesn't do quite as well. And this doesn't mean the theory is wrong down here, by the way. It's just we know that it should this particular line should mismatch with the observation. But fixing the line up to match the observations is very tricky. But I wanted to show you this not because I expect you to give you a crash course in this subject today, but just because this pattern of points in this data, if you compare these points versus if you look at the straight line, you can see there's these bumps in it, and those bumps in the straight line are also present in the data, and those bumps are the same bumps that we saw in the CMB pattern. And so these are, in the CMB, it's a lot easier to see because it's a much cleaner data set. And these are these acoustic ripples, these sound waves from the early universe. So these sound waves from the early universe were present in the CMB, but then because they're present in the CMB, that means that same pattern is present in the ripples that eventually grow up to be galaxies. And so if we look at the pattern of galaxies, and we see the same pattern that we saw in the CMB. And so it's a nice confirmation that we really do know what's going on. That we can look for this, we see the same thing in very different times. And just remember, the CMB that we see on our sky is those are not the identically same ripples that grew up that cause the galaxies we see. It's just they have the same statistical properties because the universe has both at all different times has been described by the same history. It's just we're getting different snapshots at different periods of time. So that's as you can see, this is a very powerful way of studying dark matter, these galaxy redshift surveys. But they're not the only way. Another way that's just now we're really getting good at is called gravitational lensing. And so we've known for a long time, essentially, the theory of general relativity was confirmed by its prediction of gravitational lensing. So if you try to use Newtonian gravity to describe how much light should bend, and then you use general relativity to describe how much light should bend, the difference between the two answers is a factor of 2. So that's the biggest difference between Newtonian gravity and general relativity. And the reason for that difference is that one of the central insights of general relativity is that you work with space and time. Whereas in a way of picturing Newtonian gravity is that Newtonian gravity only changes time. If you try to write Newtonian gravity, pure Newtonian gravity, in a modern language, is that it has the effect of changing the speed at which time proceeds, but it doesn't bend space. Space is absolute. Whereas in general relativity, both space is bent, and straight lines are not what we perceive to be straight, but are actually the location of straight lines is changed by the presence of matter. And the speed, the rate of time's progression is also changed by matter. And those two effects combine and make the light bend more in general relativity than it does in Newtonian gravity. And so this is confirmed by looking at the bending of the light of stars around the sun. And so you can imagine if we can see the bending of light around the sun, which is, it's a relatively small object in universal terms, even though big compared to us. Even more so than galaxies, whole galaxies should bend light rather a lot, and indeed they do. And so if you picture this, if you take this picture and then this big dip here is a galaxy cluster, labeled helpfully here, that if there's some galaxy in the background, then the light coming from that galaxy will get bent by the bending of space of the intervening galaxy cluster. And so we can get distorted images of the background galaxy because the light is going through the bent space around this galaxy cluster. So just to take one step aside, I keep saying galaxy cluster, and I'm not sure I defined it. So we all know what a galaxy is. We live in one. Galaxies are big collections of stars. A typical galaxy has 10 to the 11 solar masses of mass. So that's 100 billion. The mass in the galaxy is 100 billion times the mass of our sun. A cluster of galaxies is a collection of hundreds to thousands to tens of thousands of galaxies. And so a galaxy cluster is the biggest object that we have and that exists, the biggest conglomeration of dark matter. Excuse me. And so this is our theoretical picture. And then we can go out into astronomy and actually make a picture of a galaxy cluster. And what we can see is that around galaxy clusters, you indeed see these smeared, elongated images. And these are galaxies that are behind the cluster that we see here, getting distorted by the gravitational lensing effect. And so this is what we call sort of natural telescopes, because not only are these images distorted, they're also magnified. And so by looking around very large clusters, we can actually see further into the past, or further into space, than we could if they were not in between. Because they work like a lens, and they gather up the light and focus it. And so we can see further back. And so basically we can use these images around the middles of clusters to characterize the pattern of dark matter in the very central parts of a cluster, where it's the very central area of a cluster or a galaxy, or most of the dark matter is, or where it's the densest. And so University of Chicago Professor Mike Ladders is one of the leaders of this field, and I asked him for a picture from his work, and so he sent me this one. And so this is what we call strong gravitational lensing. That's where the light is bent so much that it gets significantly magnified and really noticeably distorted. So you get these really long arcs. And so Professor Ladders uses these to reconstruct the matter profiles of these galaxies. But I really wanted to say this not because I wanted to talk too much about the technical details of his work, but because he uses a very clever technique, or a quite unique technique for analyzing these images. Because one of the very hardest things to do is you have lots of pictures of galaxies. But it's very hard to get a computer to tell the difference between an image that has a smeared galaxy in it and one that doesn't. Because computers just are very bad at picking out this pattern. But humans are really good. And y'all can probably, without any training, just look at these and say, oh yeah, there's a elongated thing, there's another arc, there's another arc. There's an arc, right? I mean, it doesn't take any effort for us. Turns out because the human brain is a superb pattern finder. And we find patterns where there are no patterns. But in particular, we find patterns where there are patterns very, very well. And so what Mike figured out was that it's really hard to get a computer to do this. I've got a graduate student. I've got some time. And so what he did essentially was write a computer program that would show us a series of images. And the person and people would sit for hours on end and look at each one and rate it as either it has lensing, doesn't have lensing, or maybe it has lensing. So there's like a multi-step process. And in this way, he was able to analyze far more images than had ever been analyzed before, just by getting him, a graduate student, and a postdoc, I think, and then maybe one other person, to just sit and go through for tens of hours looking through images. And it worked really well. It was very good. They were consistent. They found tons more galaxy lensings than had ever been found before. So it's a really clever thing. It shows that the human brain is not, hasn't been surpassed by computers yet, anyway. But so that's strong lensing. And so, but much like the early astronomers I was talking about, the 1960s astronomers, it's not really early, I guess, but the early astronomers who were interested in the patterns of whole galaxies, we also would like to know how much matter is in a whole galaxy, not just in the central part. But the lensing that causes the galaxies away from the center is very weak, and hence called weak gravitational lensing. And so rather than getting these big distorted images, you get very mildly distorted images. And so you take a pattern that looks like this, and then it's turned into a pattern that looks like this, where you can see towards the middle you get pretty noticeable differences. But on the outside, pretty minor differences. And so one of the really big projects today is to figure out a very good way of statistically analyzing images to look for this kind of lensing. Because there's a lot, even though the other kind of lensing is more dramatic, there's far less of it. And so if we can pick out these patterns very well, and for this you really do have to use computers because there's way too many of these to do by eye. If you can use these patterns really well, we can learn a tremendous amount of information about many, many galaxies. And so this technique has already actually borne fruit. And that was in the study of this particular galaxy cluster that goes by the name of the Bullet cluster. And it's called the Bullet cluster essentially because of this pattern right here. What we think has happened in this picture is that this is one of the largest galaxy clusters that we know of in our observable universe. It weighs 10 to the 15 solar masses. That's, I'm not even sure, it's a billion times the mass of the sun. Do you have a question?
What's the significance of the blues compared to black?
I'm going to explain that. So this is a very massive galaxy cluster. And we knew it was really massive because at first, just because we looked at the galaxies, and we saw, wow, there's a lot of galaxies right at this redshift. And so we studied it more. And so it was the systematic study of galaxy clusters these days involves using multiple wave bands. And this is one of the techniques of modern astronomy. Now, I'm not really an astronomer myself. I've never been to a big telescope or anything. But I do use their work, so I appreciate them. But modern astronomy so individual astronomers usually specialize in a particular wave band. So there's radio guys, there's X-ray guys, there's optical guys, CMB people, UV people, IR people, and they all have fights over who's best. The X-ray guys, I should say, are I think the copyists. I'm not sure why, but they are. And so I think basically because they were in many ways ahead of the game in many things, but I'm not sure if that's fair. But anyway, so that's a little sociological aside. So in this, once we knew that the Bullet cluster was interesting, we looked at it in various different ways. And so one of the ways was to give the X-ray guys their due in X-rays. And so we took an X-ray picture of the Bullet cluster, and that's where you get these red shaded pictures. And this is where X-rays are coming from in the Bullet cluster. And so what you see is this two bifurcated pattern. So you see sort of a diffuse clump of gas here, and then this very distinctive cone-shaped gas here. Now, anytime an astronomer sees a cone, we know right away that the gas is moving very rapidly because this is the characteristic shape of a shock wave in a diffuse gas. And this is where the name Bullet, the Bullet cluster, came from, because as soon as we saw this pattern, we knew that something was moving very rapidly, because that's the only way you can get a distinctive pattern like this in a gas. And so, in fact, they figured out what happened here is that there's a very, very big cluster right here, and then a just ordinary big cluster right here. And what we happened to have caught was these two clusters in the process of merging. So, in this hierarchical picture I was describing at the beginning, you have big halos that slam together to form even bigger halos. And so, what we're seeing here is that process happening in real time, as it were. And so the gas in these halos has hit itself. So the gas from one halo hit the gas from the other halo, And both kinds of gas got heated up. And so that's really cool by itself. But then we did the next observation that was done was to use this weak lensing technique, which is still quite new even today. So this was done a few years ago. And so this is one of the first real vindications of weak lensing as an independent technique for studying galaxy clusters. So what we did was we looked at the pattern of weak lensing around the bullet cluster, and then used that to map where all the dark matter was, or where the majority of the matter in this cluster was. And that is what this blue haze is that the intensity of the blue shows where the matter is, where the thing that's causing lensing lives. And the black is just the black of space, and then all of the white colored blobs are optical light. And so these the thing to say about these blue blobs is that they're not in the same place that the red blobs are. And they're just significantly more displaced from each other than the red blobs are. And so in the hierarchical structure, dark matter dominated picture that I described, this is exactly what you would expect to happen. You have dark matter that's just flowed through and is only going to slow down slowly because of gravitational forces. And then you have ordinary gas clouds, or hot gas clouds, that hit each other and heat up and make lots of X-rays. And there's a displacement between where the gas is, because in clusters of galaxies there's as much matter or more matter in gas than there is in galaxies. And the dark matter, which is the dominant form of matter of all kinds of matter. And so this is the real, so people were up before the bullet cluster essentially, people were trying to dream up alternate theories of gravity where you could somehow mess around just with the gravity part to explain why spiral galaxies behave the way that they do. But those theories cannot account for something like the bullet cluster because to displace the gravitational lensing from the location of the ordinary matter, to do that, you have to have some other form of matter that does that. So this is the best direct proof we have for dark matter dominance. So
It's the lensing that allows you to infer the location.
that's correct, yes, because by using that pattern of those smeared out background galaxies, you can see where the matter that's doing lensing is. Okay, so with the last few minutes, I'm going to step away from astronomy just for a second. Because this is the one lecture where I'm going to be talking a lot about dark matter, just say, I keep talking about dark matter like I know what it is, but I don't know what it is, so what is it? And we're looking. We don't know. So I thought I should say that one of the very best dark matter detectors, it hasn't detected anything, but detectors designed to look for dark matter in the world is here in Chicago. It's Observatory lab. It's run by this guy, Ron Collard, who's famous for denigrating all of for not denigrating, I shouldn't say that, especially regarding reported. He's famous for being a very sensitive scientist who sees the flaws in both his and others' work. And puts it out apparently in high volume. He's very good at what he does. Anyway, so he's designed this really cool detector, which is currently operating in just outside of Batavia. It's in an experiment very near Fermion in Batavia, where they have this this complicated fluid. It has fluorine in it and some other stuff, and they've superheated this fluid so that it's just on the verge of becoming a gas, just on the verge of boiling. And if a dark matter particle zips through, when dark matter particles zip through this gas, which they do, this fluid, which is in this glass gourd here, which is what this picture is of, then every once in a while, not often, but every once in a while, they'll hit one of they will interact with one of these, the nuclei of this fluid, and cause a reaction to take place, which then they can see. And so this is designed to look for these very rare recoil events. And so it's called COOP, the Chicagoland Observatory for Underground Particle Fluids. And so, and this is not the only such detector. There are many of these detectors around the world using a variety of different techniques to wait for dark matter just to come along and hit us. there's some in, there's one in Italy called, what's it called? Dama. And they claim to they claim to have seen dark matter, sort of. They see something that looks like it could be dark matter, but they're not sure. Because essentially there's two ways of doing these experiments. One is to make them extremely sensitive and block out all of the background noise, which is what this approach. And so if you see anything, it's got to be dark matter. And the other approach is to design a detector that sees everything, and then just try to subtract off all the normal stuff. And then if there's anything left, it's dark matter. And that's more or less the Dama approach. And the problem with that, obviously, is that if you make the subtraction even slightly wrong, then there might be some problem with your data. And so they do see such a residual. And no one has yet figured out exactly what it could be. And so it might be dark matter. But until it's confirmed by one of these other detectors that doesn't have the background noise, I don't think anyone will really believe it. So another way to look for dark matter is directly using astronomy, is that in some theories of dark matter at least, dark matter will every once in a while, two dark matter particles will get together and make essentially, will collide and make a gamma ray. And so now that we have a very nice gamma ray telescope called the Fermi Gamma Ray Telescope in space, and so we now have a picture of what the night sky looks like in gamma rays. It's pretty quiet. Night sky is very quiet in gamma rays, but except for our galaxy, which makes some gamma rays from hot gas. And so right in the center of our galaxy, we can look, and that we know that the biggest collection of dark matter locally is in the center of our galaxy. Because if there's any dark matter around, that's where we're going to, if the dark matter is making gamma rays, we're going to see it most likely in the center of our own galaxy. And so another Chicago professor and Fermi Lab professor, Dan Hooper, who's a theorist, has analyzed the gamma rays from the center of our galaxy. And again, it's a place where we know that normal gamma rays are being made, because there's a lot of hot gas there. But he claims, and again, it's one of these things where you have to subtract what's expected, and if there's a residual, it might be from dark matter. And so in his calculations, he thinks he sees this slight residual. And so this is another hint that we might have seen dark matter. But it's also possible that the subtraction has not been exact. So again, there's a lot of these signs that we might be on the verge of actually directly seeing dark matter, but none of them have yet been absolutely confirmed. I should say that one nice story about gamma rays is that no one ever knew that gamma rays existed in space long ago. And so during the Cold War, the first gamma ray space telescope was launched, not to look for gamma rays from astronomy, but to look for gamma rays from nuclear explosions on Earth. Because one of the things that happens when you have a nuclear bomb go off is you release gamma rays. And the thinking was that, well, you know, if someone like Soviet Union or China or someone sets off a nuclear explosion and doesn't tell us, one of the ways we could see it is if we have a telescope. If it picks up some gamma rays, well, there's not a whole lot of gamma rays just flying around, and it must be from a nuclear explosion. So they made it was a very clever design. It was really basic. They basically made something like a beach ball. It had a bunch of different, well, not quite a beach ball, but just it's a bunch of flat surfaces that were gamma ray detectors. I mean, it was just a ball in space. And they're just waiting around to see if you saw any gamma rays. And right away, they put this thing in space, and they started seeing gamma rays on the not-Earth side. And so they thought, well, oh wow, there's actually gamma rays coming from space. And so this is actually, so the field of gamma ray astronomy got started completely by accident in the search to detect nuclear explosions on Earth. So it's kind of cool. And there's actually a lot of, gamma ray astronomy is a very cool subject because there are lots of sources of gamma rays and we don't really understand them very well. You can see, I mean, right here on this picture of the gamma ray sky, these little gamma rays come. And one of the interesting things, just one more momentary aside about gamma rays, is that a lot of times when there are gamma ray sources, they are short-lived, called bursts, gamma ray bursts. And so suddenly, nothing will be happening. Boom! Huge amount of gamma rays. So much gamma rays that it's as much energy as is released by the sun in a million years gets released in a second in a gamma ray. And so it's boom, it's there, and it's gone. And we don't know why this happened exactly. So they're mysteries. So just the last thing I wanted to say about dark matter, though, is that the last way we're looking for dark matter is to try to make it directly at the Large Hadron Collider in Switzerland and France, CERN. And so it's very possible that the dark matter can't be made by the LHC. And we don't know, obviously we don't know what the dark matter is, so we don't know if LHC can make it. But a lot of people would love to see it directly created at the accelerator. Not only because it would just be confirmation of the nature of dark matter, but if you can make it at an accelerator, then you can make it again and again and again and keep studying it better and better. So that's, rather than having to rely on waiting for it to sort of just like mosey on into space, you can just make your own at home as it were. Okay, so I'll finish with that and take any questions. And just before I start taking questions, I just want to remind everyone that they should turn off their cell phones. And actually, now you can turn your cell phones on. Just talk outside. And if you need to leave, feel free to go now. The talk is at the end. Yes, sir.
In this last experiment, teacher, they can tell us the dark matter particle shapes.
Right.
Dark matter doesn't interact.
It doesn't interact very much. So we think that the dark matter still interacts with the weak nuclear force. So this, I talked about this a bit a couple of lectures ago. So the weak nuclear force is the force that allows radioactive decay to occur. And so it's called the weak force for a reason, because it's extremely weak. It's the only force that's weaker is gravity itself. And so dark matter doesn't interact with the electromagnetism, and it doesn't interact with the strong nuclear force. But we suspect, but we don't know for sure, that it does interact with this weak nuclear force. And so it's just the interaction rate with that force is just really, really low. And so it can interact, it just doesn't go very much.
Can you say that dark matter is not a boson?
What?
Can you say that dark matter is not a boson?
Yes. We're sure it's neither, well, it's not, so it's not, whatever it is, it's not charged under the electromagnetic force at all. And so we usually think of bosons as, I mean, it could have, what kind of statistics it has, we don't know. Yeah, it could be either, it could be fermion-like, it could be boson-like, we don't really know. It depends on what your theory looks like to study.
So it could be a scalar that does a couple of anything but matter? Possible.
That is conceivable. The fact that the relative abundance of dark matter almost exactly matches the prediction from a particle interacting with a weak nuclear force encourages us to think that it's probably governed by the weak force. But yeah, we don't know. Until we see it directly, we don't know. Yes.
Can you explain how Newton assumed or thought that the light would be led by gravitation? What was this?
Oh, so I'm not sure that Newton ever thought about the question. I mean, maybe he did, I don't know. All I mean by the Newtonian, what I meant by Newtonian gravity is having a different prediction for light, is that if you just imagine, so if you follow Newton and think of light as a particle moving through space, and you use Newtonian gravity to calculate how much the sun, and then you know that it travels at a finite speed, and you just calculate how much the force of the sun changes the path of the light as it goes by the sun, then that answer is off by a factor of 2 from what you get in general relativity. Okay.
I am a bit confused. In the picture of the large galaxy cluster, you seem to indicate that the dark matter is localized in some way. Now, the movie picture, the video that you showed previously, showed that there is a coalescence over time of dark matter. How is the dark matter arranged or located in an ordinary galaxy? From your talk, you seem to indicate that it's fairly diffuse. Am I wrong in that? Or
No, you're right. So you're right. So it's a question of length scale. So in the movie I showed, that box was hundreds of millions of light years wide.
Okay.
And so something that was very compact there, if you then zoom into a particular galaxy, is still quite diffuse.
Fairly diffuse.
Yeah, so
It's a matter of scale.
it's a matter of scale. So the dark matter is more spread out than the ordinary matter, but on the biggest scales has compact down into a smaller chunks than the star. Does that make sense?
Yeah.
And when the gamma rays come from the center of our galaxy,
So even though it's spread out, the density actually scales almost, it scales with radius, and so the dark matter in the center of the galaxy is much more dense than it is in the outer parts. It's not a featureless gas. It follows a profile. So the density, the closer you get to the middle, the density gets higher.
So the pressure is high.
There is no pressure. So it's a pressureless gas. What it is. It's just, the thing that it's not supported by pressure, but just by, I guess it's kind of by pressure. It's just kinetic energy. So each dark matter particle is moving at a certain speed, so it's loose particles moving in a gravitational field. And so the particles, they just freely move along in the gravitational field. They don't have pressure because they don't ever hit anything. So they're just loose, free particles moving in a gravitational field. So they're not supported, they're not pressure supported. Like,
They don't have pressure because they don't interact,
Right.
essentially.
yeah, they don't interact with anything except for gravity. Gravitationally, they interact with each other.
Is there a theoretical limit to how much dark matter can coalesce, or can it eventually form a black hole?
If you can get the dark matter could absolutely form a dark hole if you got enough of it into one small space. The trick is that since it doesn't interact, it's hard to get it to cool it down enough to get it really, really into a small area. But it certainly can make it into a black hole. I mean, I think that one of the ideas for how you make very early universe black holes through some process where you get a bunch of dark matter to sort of collapse into a black hole. Because you couldn't, once a black hole is formed, you couldn't tell if it was a black hole originally made of dark matter or made of regular matter, because most of the energy density in a black hole is gravitational. So it's purely the gravitational self-interactions that are dominating. So you couldn't tell the difference between, I mean, if you just somehow you could arrange to make a black hole purely out of radiation, you couldn't tell the difference between that and one made out of ordinary stuff. Yes.
Why couldn't dark matter be made of neutrinos?
So that was actually it's called hot dark matter. So it's something that people studied a lot. The problem with neutrinos is that they don't weigh very much. And what that means, so you could, what I was going to say is it's qualitatively it works fine. Quantitatively it doesn't work because really, really light neutrinos, they basically move too fast. So you can't, to make a halo, a galaxy halo, a dark matter halo the size of like our galaxy, out of neutrinos, those neutrinos would be much more diffuse than the cold dark matter we have. And so you can actually, so people have spent a long time studying this because it would be great to use neutrinos to make dark matter because we know about neutrinos.
Why couldn't the neutrinos slow down?
You can't, so there's nothing, one thing is there's nothing to slow them down. Two, it's very hard to slow down extremely light particles. Because they just tend to, it just doesn't take much energy to keep them moving extremely fast, close to the speed of light. So neutrinos are typically moving very close to the speed of light. We know, we can calculate the properties there. And the problem, so that's the problem, is they just tend to move too fast. And so they basically gravity can't corral them into small enough spaces to match the observations we do. I mean, if you have a hot dark matter universe with neutrinos as all of the dark matter, it looks sort of like our universe, in that there are still halos and galaxies can still form. But the pattern is very different. There's fewer galaxies, and basically I don't know how much you know about the details of this, but in a hot dark matter universe, so basically instead of this, what you get is from this line about right here, it goes it dives really rapidly down. And so you can just do observations and you can tell that neutrinos just aren't doing it. But they could. I mean, conceptually they work, but as a matter of fact, they don't. Yes?
Again, referencing the movie that you showed about the condensation or collapse, that did not take account of the expansion of the universe.
Oh, isn't it?
It did.
Yes. So the way we do those movies, the way we do those movies is that we use something called co-moving units. So basically, what you do is you rescale all the distances so that the distances so that you implicitly take into account the expansion of the universe. And what that means is that, in practice, is that whenever you have a particle that's moving, if it doesn't hit anything, it just slows down in time. And that's how you take into account the fact that the universe is expanding.
So you would say then that the rate of collapse of the universe was greater than the rate of expansion of the universe at that time.
Well, so the rate of collapse of individual clumps is greater than the rate of expansion, yes. So on average, those clumps are still moving apart from each other. But so that's how you can tell the difference between something that's going to be a clump one day and something that's going to be distinct clumps. Is the distinct clumps are still on average moving apart. And moving apart in that movie means staying the same distance from each other. So I can show it here. So here's a clump here, and here's another clump. If you watch the movie of these, and they always just stay this distance apart, that means that they're in the real space. That means they're moving apart from each other. Because in this movie, things will tend to move together. If they're moving together, that means they're really moving together. If they're staying static, that means they're actually in real space moving apart from each other. And so that is precisely the difference between things that are bound objects, we call them, or halos. Because those are the things that will eventually just lose track of the overall expansion and fall in. And things that still expand relative to each other.
Dark matter goes through there. Is it a visual, or how they where do they test for, where they see it?
I don't know that much about I was trying to read the webpage and I didn't quite follow what they were saying, but most of the time those experiments are waiting for light. So it's a visual thing. You might not be able to see it with the naked eye. So our eyes are actually surprisingly good at picking out even a few photons.
Right.
If you darken a room and wait for a long time and then release just a few photons, then we can actually see that. But obviously, they don't have the graduate student like watching a dark room all day. I'm sure they thought it, yeah, probably not efficient enough. So usually they're waiting for something to trigger. I don't know what the triggering is in that one. Most of the time, the triggering is light. They're waiting for a particular pattern of light, and light is nice too, because then if you can measure the frequency of whatever's released, that'll give you some indication of how energetic how much energy was transferred in the collision. Yes.
Experiment sounds something like the amazing cloud changes.
Mm-hmm.
My question is, how do they keep it from being sensitive to all the other background radiation?
So it's underground. It's way underground, and I'm not exactly sure what they do. I know it's very.
Others would be polite to point that out.
Oh yeah, of course. Yeah, usually what they use is, the best shield is typically good. They just go down deep. So there's a lot of the time they put these into old mine shafts. A lot of dark matter experiments are deep in mines. So what? So the Batavia one I don't think is in an old mine shaft, but there's one. There's one in yeah. I'm not sure. So this one I'm not sure how they're shielding it.
It goes in the deep tunnel.
I'm sure it's in the tunnel. They're always underground. It's just a question of how deep underground they are. Like the one in Italy, the Dominal one, it's actually in the center of an old volcano, I think. Yeah, so they always use the earth to shield, because if you have to put it at least somewhat underground, or the cosmic rays kill you. Right? And so, but you can kill off most of the cosmic rays by going a few hundred feet. So minimum is a couple hundred feet. Just a question is whether it's 100 feet or a mile. Yes?
I got a kick when you actually admitted that graduate students and postdocs sat around looking at pictures and images of color research. Did they also set up for pizza and drinks?
I don't know. You can ask. I imagine they did.
You were talking about gamma rays
Yes.
as a means of detecting any nuclear explosion. Do you know, is that generally part of the process of observing if there are any surreptitious explosions anywhere in the world?
I don't know if they still do that. That's a good question. I can't imagine that it would be something they would stop doing because there's just still even now that we know about gamma rays coming from the universe, various sources. There's still not a whole lot of gamma ray sources on the Earth, so it may well still be one of the ways that they try to watch for life experiments. Though now most of the tests are done underground, right? So it might be that the gamma rays can penetrate some distance of the Earth, but I'm not sure how much of it. So that's an elaborate way of saying I don't know. So I don't.
Way back when the government of before the government of South Africa changed, and I don't know the ways they think they detected a nuclear explosion down there, probably in the ocean, and I'm not sure whether the new government ever admitted it or whether that came out, but I think they saw it in space, a flash or something.
Gamma rays would be. I mean, that's a dead good one because gamma rays go. They penetrate a lot of different stuff. And they don't. Not a lot of things make gamma rays. Yes.
This, again, correct me if I'm wrong. The COOP experiment is only looking for highly energetic photons, then?
For photons in a particular energy band, I can't really remember. It depends on it all. These always depend on the details of the experiment because I know some experiments get. I just don't know.
Okay. Because there would be a problem if they were going down into the near infrared region, because there's a diffusion from the center of the Earth, temperature diffusion, which would blind out patients.
I'm sure. Yeah, there's probably high energy. Would be my guess.
Okay,
I think it's usually like salt X-rays.
There's a website, obviously.
There is. It's not that clear. But you can. They have like their technical proposal online, which is what I tried and failed to understand. But I didn't spend that much time on it. So, but yeah, So COOP has a little page that you can look at. I think they also they have public talks on there from time to time too. It'd be interesting to know more. I stopped going to dark matter talks at some point because I went to a lot of them as a graduate student, and they're always the same, which is they go through 45 minutes of all of the details of the experiment and 15 minutes about how they didn't see anything. And so it just, it gets the same song.
Yeah.
I always feel bad for the graduate students. You write your PhD thesis, and the bottom line, you can ask what the bottom line is that we didn't see anything. So it's hard being a dark matter observer because it's very important work, but really dull. Yes.
In your handout, you refer to modified gravity and the idea that includes that gravity is stronger on longer scales than Earth scales. Evidently, the notion of modified gravity has been discounted in favor of something called dark matter. What complications are there in modified gravity?
Yeah, so the original efforts to modify gravity were made in the attempt to explain away dark matter. And so once we sort of, especially with things like the observation like the Bullet cluster, we're pretty sure that the dark matter is really there, and it's not just a gravitational effect. But by the time we found the Bullet cluster, that we also found the accelerated expansion of the universe, which gives us, if anything, an even better motivation for thinking about modifications to general relativity. Because it's quite hard to make a consistent modified gravity theory that just changes the rotation curves and things like that. And so people tried for a long time, and those theories are always kind of ugly. And admittedly, the modified gravity theories that explain accelerated expansion are pretty complicated. But So the modern picture is that these modifications of gravity, what they do is basically the reason for existence is to explain why the universe is accelerating now. And then the consequence typically is that whatever you introduce to make that happen also has the impact of making the gravitational force stronger, about a factor of a third stronger in between galaxies today, as compared with just general relativity by itself. Does that answer the question?
Well, do any of the modified gravity theories include the idea that the strength of gravity may fluctuate depending on the distance?
So that's hard to do because, so if we want to describe it using a fundamental law, so we're always looking for like a new fundamental law of gravitation. And so the way that fundamental laws of forces work is that there's something carrying the force, so some particle. And so that particle will then just have some properties that depend on various things. And those are always things that depend on like the distance or the density. But to put in some other modulating effect would be hard to. I mean, you can do it sort of by hand, but it's hard to motivate it with some fundamental principle.
But neutrinos fluctuate in transit.
Well, so they fluctuate among. So they do. So that is a particular physical interaction where they don't. What they fluctuate is among the kinds. So you go from electron type, muon type, tau type, and you sort of you can change your stripes as it were, but they don't change. They're not. The neutrinos are not force carriers. They're matter. They're a form of matter. So but the force carriers, like the graviton or the photon, none of those. I mean, I think that the two different. You can probably change from being a W boson to a Z boson. Those are the two force carriers for the weak nuclear force. I think there are various interactions that can change those kinds, but it doesn't really change the strength of the force very much. And so, I imagine you could dream up a theory to cause the force to fluctuate in time, but it's hard to know why you would want to do that. Do you have an idea? Is there a reason you want to do that?
Well, it seems like you're not multiplying entities. You're restricting yourself to, the normal type of matter. And just, if it's simpler just to make modifications of gravity than to create a whole new type of matter, it seems like...
We make kinds of matter all the time, too. They just don't help us very much with the dark energy problems. Believe me, physicists will invent a new kind of matter at the drop of a hat. Whatever. So, the problem is that the dark energy is not a form of matter. It can't be because it has negative pressure. And so we can't explain that problem away by changing the matter content very easily. And so whatever we need to do is end up looking sort of like a part of the force law. That's what we think now. Maybe we just don't know the answer, so it could be something else. But that's the general thinking. Okay, that's right.
Now, I wanted to know why you said that the graviton is a force and not, as I understood, that it's the one that deforms space and time.
That is in a nice concise statement the fundamental problem of quantizing gravity. And we don't know how to do it. We just don't know the answer to that question. It's that when we describe the classical theory of gravity, that is the theory of a smooth field, then that we can get a very good intuition for how gravity works by describing space being deformed. That works really well. And then if we want to go to something like a quantum description to describe it the way we describe the other three forces, then we have to talk about individual particles doing things. And how we connect those two intuitions is one of the fundamental questions of modern physics. So we don't. Probably the way to think about it intuitively is that a particle can be thought of as a wave, and so that wave, in some senses, is a small ripple in space-time. And so, if you have a large-scale deformation of space, then that would be, in a sense, sort of the collection of many, many, many waves that have built up into a large structure. And so in the same way that or in a way analogous to, so what's a good example? So in the strong nuclear force, there are particles that are called glue balls, and so the force carrier of the strong nuclear force is called the gluon, which is a funny name. But we know that a bunch of gluons can form together into a particle that has no matter in it, no ordinary matter in it, no force, but nonetheless carry energy. It's just trapped strong nuclear force energy into something that looks like a particle. And so, in an analogous way, the gravitons themselves could form a sort of condensate. So these little ripples, these little individual particles, form sort of a huge condensate